Students to lecture number 5, scenario planning. So you've seen that in this course sometimes we have to assume numbers, and very often I get the question, how do I assume the discount rate, which consists of 3 parameters: the interest, the risk, and the inflation. Well, the inflation is a very easy one because, at least in Europe, the European Central Bank tries to keep the inflation rate somewhere between 2 and 3%. Sometimes it goes a little bit below, but you can find the inflation very easily, what the current inflation is, and otherwise you can also assume somewhat 2% per year. But for example, interest, it becomes a little bit more difficult. Yeah, because the interest depends largely on how big the money, the sum is that you want to borrow, and also for what purpose is very important. So we've seen that, for example, when you want to buy a house, that yeah, you will borrow a large amount of money for a long period of time, and this gives the most stable results for interest. They don't fluctuate as heavily, for example, as short-term loans or loans for smaller amounts. So, for example, you could have a look at mortgage.nl, see the link below, and you can actually find mortgages interest rates for different banks. This is an example of 2019, but obviously if you click the site, you will see the latest numbers, and there you will also find different interest rates for basically the duration of your long-term loan. So it says variable, 5-jaar vast, 10-year vast, and that basically means like, okay, do you want to have like a variable interest rate that changes with the market every year, or do you want to keep your interest rate fixed for a certain amount of time? Which can be interesting if you think that the interest rate will go up in the coming years. For the risk, that's the last one that is included in the discount rate, that is usually an extremely difficult one and falls a bit outside the scope of this course. So you could use, for example, 0.5% and source that back to me. Later on, you may dive into this subject more deeper. You may remember this slide from the first lecture that I gave you. It contains all the entities, the economic entities. And here I also put down the different types of interest that those entities pay or receive. So you can have a look at the numbers where you can see, okay, how much tax, for example, needs to be paid or received. If they would go to a bank, how much would they then pay on loan interest? And you see that that differs largely between the entities. And that is, of course, because there's a different risk. So for governments, there's a typical low risk that they're not going to be able to pay back their loan. Therefore, the interest rate is low. But for example, businesses, and especially large businesses, which are not privately owned, the risk is much larger, or can be much larger. The risk is actually expressed in a number 1 to 5. See the table. So let's get back to the estimation assignment that we did last week. Some 10 years ago, I worked at a company called Van Remme Ultraviolet Technology. And what we basically did, we sold these kind of reactors that you see in the top right, which actually can treat drinking water with ultraviolet light. This ultraviolet light is able to disinfect the water, So, for example, you could actually completely replace the use of chloride. Um, but you can do much more with it. You can also, for example, break down very difficult molecules, such as cyanide. If you use a combination of ultraviolet light and hydrogen peroxide, you can actually break cyanide down in a fairly cost-effective way. At least that was to be seen, because it was my task to create a special pilot installation for a company in Amsterdam to do so. So we knew that it works in theory, but we never know in practice how good it will work. So I was working at the research and development department, and I had to do the engineering, the installation, buy the materials, do the quality control, the transport, and I had to make a model that includes all the capex and opex, like energy, chemicals, and maintenance. So I designed a unit which has 5 ultraviolet reactors based on the theory, and actually the whole scheme can be found on the lower right. Yeah, so then I of course needed to also make an estimation of the budget. So how much would it all cost, and how much would it all save the company if we could actually break down this cyanide, because they did not have to pay the treatment cost to the water board, etc. anymore. So actually, what I actually had to do is I make a very big model. There's, for example, a couple of known and unknown parameters which I had to do assumptions for, and then calculate what the outcomes was. So I made a fairly big Excel file for that. Then I could also know what all the components were that I needed, so I could go to the market and make a list of capexes. Of course, there's also a very big unknown variable, which is the reaction speed between the ultraviolet light, the peroxide, and the cyanide. And that was something that I needed to figure out in practice. So after my pilot was built, because of course it depends on temperature and pH and whatnot. So I had about 1 or 2 years of time to figure that out in a small scale pilot plant, and after that I could build a full scale plant. And of course the small scale plant could already give me an indication about the cost of the bigger plant. Yeah, so then actually during that year I could see my results and fine-tune, turning the wheels here and there to see if I could optimize the whole system together, and maybe put an extra ultraviolet reactor or dose less peroxide to make sure that the optimal conversion could take place. And this was actually used to make a full-scale reactor for this system. So I think the small pilot scale was about 100 liters, 200 liters an hour, and the full scale was several tens of cubes per second. In the end, we could build the full-scale reactor, and we could already on forehand know quite precisely what the cost would be. So what we would have to quote to the client. Of course, we add our personal profit to that, because the staff is not free either. So we have been covering the topic of estimation, and we have covered the topic of modeling in the past few weeks. So what's left is scenario planning. Let's say you're a master of ceremony to a friend who gets married in September in a beautiful garden. What are the scenarios? And of course, you have to arrange everything. You have to maintain contact, and of course, you want it all to be perfect. So, what are the scenarios? There's a small chance that it's maybe going to rain, or that it's cold or very windy, or maybe it's very sunny or even very hot, which is possible in September in the Netherlands. So actually, what do you communicate and what do you do? Well, therefore we have scenario planning. we can actually plan for a hot day, and we can plan for a rainy day in the same time. But you have to take different arrangements at the same time, and you actually compare them together. So, as a master of ceremony, it may be easy to plan for those three different scenarios, so that you are able to switch to the rainy scenario if suddenly clouds and rain are coming. However, yeah, of course, there's other situations where it may be much more difficult to yeah, to switch between scenarios, or it may not even be so easy to think of all the scenarios that may happen. So an example of that is the IPCC, International Panel on Climate Change, which of course also plans for different scenarios regarding climate change. Here there's just 4 scenarios where they actually calculated the consequences when a certain amount of carbon dioxide and other greenhouse gases are emitted in the coming years. So there's a worst case scenario where probably the temperature will rise much faster than scenarios where we will dive into environmental awareness much faster and try to yeah, to convert to a more circular bio-based economy, more sustainable practices, where probably the amount of greenhouse gases may at some point come to a standstill, and that will also limit climate change, hopefully. But with these scenarios, and why do we do that? This is the big question you have to ask yourself, is that we want to be able to mitigate. We have to at some point know when people have to abandon islands, or when we have to build dams, when we have to broaden rivers and take other measures to overcome the consequences. And this can be done by actually planning for multiple scenarios that we can switch to a different variation. So let me just give you another example of a situation where scenario planning can be helpful to make decisions. A couple of years ago, I worked at Altero in Apeldoorn. That's a company that actually deals with green waste. And from the green waste, there's a lot of wastewater coming that needs to be treated. So back in the days, there were a couple of options. We had the current situation. In the current situation, we actually didn't do anything with the water. We just brought it to the water board and paid an amount of money for that. But there were also possibilities to build a treatment plant ourselves on the spot, which obviously would reduce some cost, and then also, yeah, of course, we would actually have to invest in that and operate it. But in the days, there were also options to create an algae pond that could deal with part of the pollution, with the algae being the ones that eat the pollution, because there's a lot of minerals like nitrate, ammonium, etc. Then there was also the possibility to create an algae bioreactor, which is actually an improved version of an algae pond with tubes. So I actually made different scenarios for those. So I called the current scenario, I call it A. The conventional treatment plant, I call it C on location. And then combinations of scenarios, like, for example, the treatment plant together with an algae pond, or the conventional treatment with the algae bioreactor, the ABR. So there's a couple of factors to steer for. For example, yeah, we needed to remove the COD. Also, nitrogen and phosphorus needed to be removed. And then, of course, there were different numbers for the amount of capex and opex that need to be paid. In the effluent cost, you can see how much money would still need to be paid for the effluent, for the outstream water. And in the end, I made a column to be able to exactly compare the scenarios together. And what I actually did is I compared all the scenarios based on the amount of euros that we would have to pay per cubic meter of water to treat the water. So here you can actually see that the current situation, we paid about 800,000 euros per year. So if you divide that over the amount of cubes that are treated, the current situation and the reference scenario, as we call it, would actually cost us €5.74 per cubic water of water that needs to be treated. But if we would actually put in a conventional treatment plant ourselves, then we would actually reduce ourselves 80% of the oxygen demand and 50% of the nitrogen and phosphorus. But of course, that would have a capex of 120,000 euros and an yearly operational cost of 60,000 euros. Then the effluent cost to the water board would significantly be reduced to 223,000 euros. And all in all, that will result in a comparison cost of €2.89, both of course paid by us, by our conventional treatment plant, and partially paid by us for the water board. So that was actually the best scenario. Still, in the end, we wanted to check whether it would be possible to go to higher removal rates, so we don't have to actually pay the water board anything anymore, and see if that would be cheaper. But the investment cost on the algae pond and the ABR were actually so high that in the end we would actually have to pay more. Still, the conventional treatment plant with the algae bioreactor would be the second best option, where we would then pay €3.15 per cubic of treated water, and we didn't have to pay the water board anymore. So this is actually why you do that. So you put it all in one big table, and you find one column where you actually can compare all your scenarios together to be able to make the best choice. So now it's time to introduce you a new capital budgeting tool, and that is revolves around the topic of last week, the net present value, or in Dutch, netto contante waarde. The only thing that we're doing with this capital budgeting tool is that we bring all the costs and revenues back to today, and we will see which of the projects has then the highest value. So how much is the return in euros of these projects, and then the highest one wins. So the highest one is the best profitable one. This one takes into account capex, it takes into account opex, it takes into account revenues, just like the break-even point, but it also takes into account the net present value. So what are all these values worth today? So we are having a much better comparison of the costs and benefits. What you have to remember for the present value is that all the cash flows in the future are less worth today. So if you bring them to today, they will become less high. And if you bring the cash flows to the future, they will increase. If you want to know about more about this capital budgeting tool, please watch the video which is in the link down below. So just a small example again to refresh your memory. Suppose we have a project where there's a certain amount of money that we revenue each year, and we already have subtracted the OPEX for you. So every year it revenues €100, and the initial investment is €300. So in net present value, we call it in year 0 we have minus €300, and then in year 1, year 2, year 3, 4, 5, we will earn €100, right? And 5 years is the duration of the project. Now, how much is the net present value of this project? Yeah, that means that we have to calculate all the from all the values the net present value. Well, we start, of course, with our initial investment, which is €300, but we don't need to bring it forward or backward because that happens in year 0. Yeah, so we don't have to do anything with that. The 300 euros investment stays 300 euros. But then after 1 year, we receive 100 euros. But we know that the present value of 100 euro received in 1 year from now is actually less. So we use the formula and we will calculate that with a discount rate of 10%. The net present value of 100 euro next year received is now worth 90 euros and 91 cents. We do the same for year 2, year 3, year 4, and year 5, and we list them here below in this list. So the 100 euro we receive in 2 years has a net present value of 82 euros, etc. And we actually sum those revenues all up, and we see that receiving 5 times 100 euro in the future actually revenues us 379 euros and 8 cents instead of what you would actually think that it would be 500 euros. Okay, then we need to, of course, subtract the capex still from that, which is the 300 euros. So we will see that the net present value in the end of this project is 79 euros and 8 cents, which is, of course, not so much, but it is, of course, still positive. So this project is going to generate money. If you do this for 2 different projects, you can see which one is the highest and which one is the best to invest your money in. Just to repeat for you the 3 easy steps of net present value. Identify the amount and timing of relevant expected cash inflows and outflows. So basically what I always do is I start with the yearly revenue and I subtract the OPEX every year, and I see when they exactly happen over the years. Then step 2, find the present value of each of those expected cash inflows and outflows. So you calculate them back to today. The netto contante waarde is calculating them to the right now. That means also that the capex, which usually already happens in the now, don't have to be calculated back. It just stays the amount that it is. Number 3, you sum all those values, all those present values up together, and then you will receive the net present value of your project. So now it's your turn. I have an example here of a project, of 2 projects, from which you can calculate the net present value. Project A lasts for 3 years and project B lasts for 4 years. The invested amount of project A is 500,000 euros. And that is the capex, and that happens in year 0. There you see the net revenues. So I already subtracted the OPEX for you from them. So there's a cash inflow in year 1, after year 2, and after year 3. For project B, the invested amount, the capex, is 300,000 euros, and I've listed the cash inflows also in the 4 years to come. Again, this is the net revenue, so this is already the revenue minus the OPEX. I already did that for you. And now the question to you is, what is the net present value of project A, and what is the net present value of project B? Now you can pause your video, and then I can give you the answers. This is the answer for project A, and this is the answer for project B. Now you see which project is actually the better one to invest in. So here's another example to calculate the net present value, to practice yourself with this. And this time I would like you to make this exercise in Excel. So put a new tab to your case studies file and add this assignment to it. In the next slide, you will find the answer to this exercise. So this is the answer to the previous exercise. And note that you can actually use the formula that I given to you earlier, but you can also use Excel to make it much easier for you, and we will explain that in the workshop. Excel has a net present value function automatically built in. See if you can try to calculate the net present value of your project with the net present value built-in formula of Excel. This was it for today, and I hope to see you in the video of next week. Bye bye.